Okay, I think today we'll just start, and then as people come in, we'll just carry on. But the point today is we are going to try to build our own autoencoder Hopfield network using, well, I will use Jupyter, I will use the Google Colab, but you guys can use whatever software you want. But if you go to the, wait, switch over to this. If you go to the NTU Cool for today, we have, so last week we talked about some principles, the theoretical background, okay? Later on, I will finish up. I know there was one last bit about the proof or some interesting analytical trend about the Hopfield equations, all right? To just briefly go through, but that's not important. It's just for you to know. You don't have to know it or do anything mathematical for the course, okay? So, but it's good to know. More importantly is today, the main goal is to actually instantiate kind of a auto or encoder, or what we know as the Hopfield network, based on what we talked about last week, last week, okay? So this is this week, and if you later on, if you want to follow along, this is the link to the Colab, okay? You can go there. And also, that's last year's video, right? So actually, yeah, I'm sure you all have known, okay? Last year's videos are all there, okay? And I think it's, yeah, I should make this note. I think it's helpful to view last year's video first before coming to class, okay? Rather than come to class and then view last year's video and then I upload this year's video. I think that's kind of very wasting time, because this year we covered the same thing as last year's video. So it's like watching the same content but presented twice. I think we don't have to waste that kind of time. So I think it makes more sense that you watch last year's video, each week before each week's lecture, so that when you come to class, you can ask questions to clarify concepts in the video. This year's video will still be recorded, and then I'll put it on, and then we can, maybe there are some, because you might ask questions or some new content comes up, then you can use this year's video to catch up on new stuff beyond just the last year's video. That's really the point of these videos. Otherwise, it's no point seeing last year's video and then seeing this year's video and then repeating the same content over and over again. It's kind of, I don't know, it's too much time. Each class is 3 hours long, okay? So that's 6 hours, So I think it makes more sense just to coach you guys about how to use the resources that are on the NTU Cool, is that you have last year's video, watch it, and then come to class with questions. And then in class, we can engage more with the coding and with the practical aspects. Actually, that's what I hope to do for the third week of the autoencoder, is that in fact that is more lab period. I'm not going to lecture so much. I want you guys next week to be like each of you using maybe a screen or so, okay? And then working through the assignment 1, okay? And then I can guide you where you get stuck on assignment 1. So that will be next, just to preempt, that will be next week's format, okay? So this week I will show you how I do it in Colab. Next week you'll be lab, and then you do it. And then, the videos are there. You can view it offline on your own time. And I think that will be much more productive. And I think you will encode things much more clearly, okay? Than just I lecture and then you just watch the video and then repeat. It's no point. You have to do it. Then you will learn things more concretely. Of course, some people's schedules are in conflict, so I know some people are having other meetings today. So the videos are useful for you to catch up if in case you have to miss a lecture. And that's fine, I'm fine either way. But yeah, so this, just to let you know, this is how we are going to dive into the next 3 models now, from Hopfield to the backprop to the unsupervised learning. This is going to be very repetitive format for the classes to the end of the semester. The first few lectures involve more lectures because we have to develop some initial necessary groundwork, okay? So that's always been like that. But from here on, it's going to take a much more practical turn. Okay, so this is to highlight to you where we are. And as I said, I want to finish up a little bit on the theory of the auto-encoding or the Hopfield network, which I didn't have, was not able to do last class. And it has to do with the notion of proving or considering why the Hopfield network works. I'm not doing this from my perspective. I'm actually just copying what is in the Hopfield's, John Hopfield's paper, the Nobel Prize winning work as we talked about. Actually, have you all read it? Try to read it. Just try. How many pages do you read into? 1 page. Or you read the whole thing?
I find it too difficult, so I read something else.
Oh, okay, good. What did you read?
This YouTube video.
Yeah.
About the Hopfield.
Is it about the paper or like some other people's own development?
I think it's just the concept of the
Yeah, the general concept. Okay. Anyone kind of put the PDF into the AI and then ask the AI to help you? You can do that, you know. No? Try it, go back and try it. I don't know. I'm curious to see if you learn that way. I certainly learned that way now. I can put the PDF in and ask the AI questions. I still try to read the paper, of course, but I find it faster actually, right? I read it first. I know there are certain things I didn't get, and then I let the AI tell me, and I verify again. So it's like, you know, at least 3 loops of that. As opposed to last time, we have no choice. We just have to painfully read the paper. And if you don't understand, you don't understand until you know, it's slower, right? You have to wait until you can ask questions. And then imagine last time we didn't have Google. You know, everything was, we line up at the library, we borrow the paper and we photocopy, and that was it, right? You know, so now we have all these resources. It's really quite amazing. So that, you know, John Hopfield's paper, try putting it in the AI and then see what it gives you. Everyone's AI will be different because it, you know, it knows your history, what you know, or rather how you interact with it. So it will be catered slightly differently, but it might be, I don't know, a better way to learn for each individual, right? Yeah. Okay. So in case you don't know, the first part of the Hopfield paper is okay. Kind of tells you about the psychology, which is what we did last lecture. And then after that, it tells you about the model and how it implements it. And then at the end, or somewhere in the middle towards the end, there's some proofs to kind of like show you or demonstrate to you from an analytical or mathematical point of view why the Hopfield network works. In my opinion, I didn't think that was so necessary. I mean, I think it's an important part of the paper and it helps, of course. But I think the proof to me is okay. There are better proofs. For example, the backprop proof for the next model, I think, as a mathematical proof, makes better sense. Okay, but this proof is okay. It's good, but it's like it seems to me still, how do you say, informally or psychologically not so satisfying still. So maybe after I share it with you, you still feel a bit weird. I don't know. I still feel a bit weird. But that's how he did it in the paper, or how his reasoning went in the paper. And there's nothing wrong with it. It's fine. It's just that, you know, you thought there'd be even more. And I think there's more. So actually, if you go YouTube, they might have better proofs and all that, or better ways of visualizing things. And that's great, okay? But just to deal with Hopfield's original paper, I think is worthwhile. So let me just go through this quickly, and then later on for the next class, next part of the class, we will be doing the more practical stuff. So this is the autoencoder proof. And as that instantiated by Hopfield himself, okay? And as an autoencoder, as we talked about, and you'll see as you implement it, it's actually an attractor network as well. By attractor, we literally mean that it attracts certain inputs into some fixed states, okay? Kind of like a gravity a black hole, if you want to put it that way, okay? A gravity point, and if you put things, it will just drop into that hole, okay? That's an attractor. And in fact, doing that is sort of like an autoencoder as well. These are all very overlapping concepts, okay? To be clear, it's not exactly that they're always exactly the same. There are different types of attractors, different types of autoencoders. But these different functions do autoencoding, do attracting, okay? So different types of functions do autoencoding, but they may give you slightly different results. They may do attracting, and they may still give you slightly different results. But they are all called autoencoder attractor because it's about having slightly different states and then regressing towards a few common states. You'll see it in the application. So autoencoding, how do we prove that? Well, John Hopfield says, let's start by making that, or saying that we have a set of input vectors, AI, which has several states S, okay? And the input vector has k nodes, right? So the last example we had, I think we had 5-bit word or a 6-bit word, and therefore k is ranging from 1 to 5 or 1 to 6, okay? And states would be different patterns of these 6 nodes, okay? So I think we had 4 examples, right? Cat, tree, cotton, something, right? And so there were 4 words, 4 different types of concepts. So S would be ranging from 1 to 4, okay? So we're okay with that. Oh, at any point, if you get lost, just let me know, okay? So the way to do it is important because it also is the way to think through how we are going to convert this into a code and into a proper project piece, okay? In a sense that, so let's make this very clear, right? So for A state 1, okay, we have the input for node 1 to node k, all right? And we might have many states. So we have state n, the nth state S for node 1, okay? And the nth state S for node k, all right? So this is the array. So Hopfield starts with this notion, okay? So imagine this is the universe of information that this network has to remember, because it is about content addressable memory. And so there's different content in there, in this universe. So how do we squeeze all this into the network so that next time when we ask the network, it can give us back the respective states, okay? So that's the problem, right? So in a sense, he has set up theoretically the data table. This is the data table, okay? So that is the S, which is the number of states, which is the columns here, ranges from 1 to n of S, number of states, okay? So this is input states. And then K, which is the number of nodes, n of K, the number of nodes, is the input nodes. Okay, and also we will have R, not shown here, but subsequently, we have output or output state nodes. Okay, this is the subsequent activation states of nodes, of the network nodes. Okay, this is a bracket here. Okay, so we can set this up, and we just have to realize first the notation is important, and so to get you familiarized with this way of saying things. So we have an array, okay, no problem, it's matrix, and then we have this little weird E sign, reverse E sign. It means that the variable S consists of all these different states, okay? So S has all these states, K has all these states, R has all these states. So this sets up the entire sets of variables that will be going into our code that we need to work with, okay? And this is the universe for this network. To auto-encode, so here is the reasoning thing here. To do auto-encoding, really what we are saying, this implies that what we want to do is make the output that we get eventually to be equals to the input that we give it, right? If you remember something, it means that if I give you the thing, you will retrieve back the same thing. That is, means you will remember it. If you don't remember it, means I give you something and then you give me something else, correct? That is the definition, okay? So this is not, this is an ideal. It's not that we are going to make it exactly equal for sure, okay? But this is really what we mean, right? When we say we want the network to do autoencoding and to do content addressable memory retrieval, okay? So that's the goal here. Specifically, in Hopfield, AJ, right, is equals to the max according to the Hebbian and the binary ReLU rule, right? If AJ is equals to the max, the sign of the input, all right, and the weights, which we talked about last week, okay, and this is the familiar function for the binary ReLU, right? Any output state AJ is going to be equals to is a max of the products of the input and the weights connecting it minus some threshold, and that's the binary ReLU. Okay, just a footnote here, just to remind ourselves. So in other words, AJ is going to be either, in Hopfield's case, is easy because this kind of relationship means everything is either going to be a 1 or a 0. It's a binary world. It's either on or off, all right? And so in that sense, this is the idea here is that we want to make AJ equals to AI, but in Hopfield's network, AJ is equals to the max of the sign of the AIW minus theta, right? That is how the network was implemented. And he's saying that this works. This is going to still allow us to do AJ equals AI eventually, according to this, because he also implements, and that's the Hebbian rule coming in, that Wij, this entity here, okay, this expression there is equals to 2ai minus 1, 2aj minus 1. To be specific, 2aik and 2ajr, right? Okay, so this is the setup here for the proof, is that the claim is that the goal is we want to make AJ equals to AI. Hopfield specifies that, well, we can do this if we first start out with making AJ equals to the binary ReLU function of AI and its weights connecting to AJ, all right? And note, what this means is that for every node, I can run out of colors, but right, what this means is that every node is connected to every other node, but except itself. Okay, right? So that's the Hopfield setup there. Okay, and he's saying that if I set up a model that has this sort of connectivity in terms of the W's, when I equals j, W is 0, right? That's what that means. But everything else is connected. It's non-zero otherwise. And the activation function is set up such that AJ is at first this binary ReLU function of the AI by the weights. And the weights themselves change according to this Hebbian function. Then we will have a case where actually we will approach AJ is equals to AI. Why? Okay? Why? Just because he says this is true or has set it up, how do you magically know that that is going to give you the case? I can try all sorts of infinite number of functions. You got to think, right? I have so many functions. I have so many activation functions. I have so many learning rules. What's so special about these two, if you put it, that it will approach that kind of thing? And you have to appreciate this because the goal here is to make AJ equals to AI. In contrast to backprop next model, the goal is not to make AJ equals to AI, in fact. Okay? You'll see when we get there. But for now, this is the special goal of Hopfield network. Okay? Okay, so we've set that up. So how do we proceed from there? So let me express that again. So AJ is equals to the max of the sine of AI Wij minus theta 0 like this. Wij is equals to 2a I minus 1, 2aj minus 1. I'll call this equation 1, call this equation 2. I am going to put 2 into 1, like this, okay? And so then I will arrive at yes. Let's call this, for simplicity, the function of AI. It's not important, but just to, there's something very complicated, we simplify it like that. Note that A of states of J of R, now this is different from A of states of I of K. This is the input, all the possible universe of inputs that this model could possibly encounter. This is all the possible states that this model could possibly give you. Okay? All right? It's going to be, because of the f of AI Wij, is therefore going to be the sum over all states that this model will experience over the sum of all the input units that there are using the function AI, like this. Just for simplicity, that's why we have the f function there, where k is not equals to r because of the two units are not, the same unit is not connected to itself. Okay? All right. So then let's expand this again. If you are okay with that, that actually what we mean is we put let's call this equation 3. Okay, we put equation 3 using equation 3. We have therefore, max. It's always good to write it out so that you can be clear what you are dealing with exactly in the formula. Okay, no problem. This is just replacement and expansion, and then reminding ourselves again what we are dealing with. Now, to be specific, this is actually ASIs of k. All the possible states, output states, as a function of all the possible input states. Okay, the whole universe of stimuli this model encounters, will give you the whole universe of outputs this model will express itself. So when we expand it, let's carry that through, okay? So this is going to be SIs of k and ASJs of r. It's important because that's why we can say we have to qualify that where j, again, k, where k is not equals to r, all right? So that if we simplify, AS j's of r is roughly, approximately, we take this component out of the summation, okay? Because of the k here, this is not, no k in there, so it becomes a constant, right? This element here, this component here has no k. So with respect to k, this is a constant, correct? So we take it out, correct? Got it? This is a mathematical thing. Okay, no problem, right? Okay, then we note that this part has the k part, yes? And so this is Hopfield's cool trick here. He puts a prime here. Let's just do some weird mathematical trick. This is where I'm not satisfied, but okay. I don't like mathematical tricks. It's smart, but sometimes it's like, well, it's just a trick. It's like, you know, you just did it this way. It's not a guarantee. You know, it's like you just try and you were lucky, so to speak. Okay? But good, it's a very insightful luck trick, okay? It's a the prime means something, okay? Okay, so he has this part where he puts this prime here. It's very important. And here there's no prime. So in other words, although we shift things around, and you can see how it's shifted around, there's nothing tricky about the moving the constant out and seeing this in another form. The brilliance is that we started with the AW as one thing, but we realized that W is comprised of AI and AJ as well. So he just moved it, expanded it, and then moved the AJ part out, and so that the right side is just the AI part only. And the AI part has summations over k, and he imposes a trick where he says, well, even though there's an AI, you know, that you think you can combine them, but for now, let's not combine them. Let's treat it such that the whole universe, okay, consists of a prime part and a non-prime part. What does that mean? We will see this trick play out later, okay? In fact, let me write it out again in the next page. So let me rewrite this. Continued. Okay. ASJs of R is approximately equals to, or is proportional to the sum of 2 ASJs of R minus 1, sums of K, 2A prime S, I's of K, and, oh, sorry, no 2 there, just this first. And then the 2A S I's of K minus 1, like this, all right? And what does this mean? He puts the prime there to say, when there's a prime, let's treat this as the part of the universe that is other, okay, temporarily hold this notion that in the universe there is the other part and there is the self part, okay, or the current part, current state. How to imagine this more concretely? So imagine that you are now seeing a cat and you want to encode a cat, okay? So currently there's a cat. However, the universe has also other things that are not cat, correct? But it's also part of the universe, okay? So we can construe or think of the universe as consisting of, for a given example of a cat, a current cat state as well as a current non-cat state, correct? That's the totality of the universe. You have this thing and the not this thing is the universe, okay? In binary world, it's like that, right? Okay, so if you think, so this is a trick, right? It's like, so like, 麻烦, why you want to think of things so complicated, you know? But using this, so any questions about that? That is the very important part. That's where I spent a lot of time reading and didn't understand it for a long time. And then you have to think about it, and then you kind of work things through, then you sort of unsatisfactorily get at, oh, okay, just doing a trick and then working it out, and then so it works that way, okay? All right, so then let's play it out. Let's imagine that right now, indeed, if this model, and we want, if this is the case, that remember, the goal is to make Aj equals to Ai, right? And so where Aj, all the possible activity is this weird function that consists of encoding all the other states as well as the current state, okay? So then what happens? If you imagine that the S prime is not equals to S, so in the universe there is cat and non-cat. Let's consider what the activity, all the possible activity this network could give you when it keeps seeing non-cat. Okay? So what does this activity look like? That is current state is not itself. Okay? Let's imagine in binary world, there is only 4 possibilities. Now this is not the same as the Hebbian rule pairing, okay? This is about the states of the activities of the input units. Okay. In binary world, there are, again, very neatly, only 4 possibilities. Given that, and this is not saying that this is cat, this is saying that for a cat state, a unit might be on or off, right? A unit might like cat, might not like cat. So it could be on or off, or on or off, okay? A given stimuli coming in might be signaling a cat feature, which is 1, or not signaling a cat feature, 0. But these all features are part of the non-cat. So in other words, even though I am not seeing a cat, some cat features might still be stimulated, right? Like cotton, the fur is stimulated, but it's not a cat, right? Okay, so this would be the possible cases of a particular feature. Now I am a cat node, right? So I like cats. So when I have experienced a fur kind of stimuli, and I like fur, okay, my result is going to be 1. This some state of activities at that moment, right, it's going to give me a 1, all right? But when there's no fur and I like fur, it's not going to be active. When there is fur, but I like fur, in that, if I am a unit that doesn't like fur, and then there is fur, right? It's -1. Why I keep writing it so big? Okay? And then just to complete it, it's going to look like this. Okay? 1, 0, -1, and 0. Okay? This part of the equation, the right side. And remember, this is not about the Hebbian rule. This is not a Hebbian rule. This is this equation working itself out in terms of the possible states that the input part could arrive at in relation to when the external state is not the current state that I like. Okay? Assuming that I exist already, that I have learned something or I have a particular preference with respect to the external environment. In terms of our interaction, I'm going to have this expression on the right is going to have this only this range of activity. Okay? Now, you take this part. If you sum over S, where S is 1 to 4, and it can only be these 4 possibilities in the universe of binary states, okay? Is what? What? Zero. Okay? Implies that the expectation, E here is expectation, when the external states are not the same as the states that the internal model likes, the expected states of, remember, this is about J. Okay? It's about J. You put that in. If expected state of AS prime I times 2 ASI minus 1 is 0, what is the expected state of ASJ? If this is 0, that is 0. Expected ASJ is 0. Okay? And this, if we go back, remember, yes, this is the function. AJ is the result of the function of the product of the binary ReLU function. So in other words, this is what Hopfield is trying to prove in a very tricky way, is that for the parts of the universe that are not this item, that are not cat, the response, the network's states towards those other possible items on expectation on average will be 0. The activity, you might have sometimes up, sometimes down, sometimes 1, sometimes 0 on a whole, but on average, all the units' activities to not cat is going to be 0. Okay? Okay? Okay. So if this is okay, then this solves the part in the sense that the auto-encode part in a sense that do I falsely recognize things that are not what I'm supposed to recognize? The answer is no. Okay? I don't activate when it is not cat on average. Okay? So this solves the part of the false memory part. If this thing is not what I'm supposed to remember, do I remember it? No. On average, no. Sometimes I might, but on average, no. That's what this means. Okay? Very tricky and very I'm very not satisfied, but that's what this means. Okay. Then let's go to the part where it is supposed to be something I remember. Do I remember it, right? On average, do I activate towards it? Okay? So is simple. Then the alternative, when S prime equals to S in this case. So current state matches self-state, matches what you prefer, what this node or this unit likes. Okay? So again, let's put that equation up here. S prime I k to AS I k minus 1. Because A prime as I k is exactly the same state as 2 AS I k. In this case, we can do this, but I think it's trivial, it's not so important. But what that means effectively, we can combine them. I don't put the square here because it's a vector and I don't want to confuse people, so I'm just going to, but effectively, you can treat it like that. Okay, what this means is that because this is the same, this expression is trying to tell you that because it's the same, you can see that they are kind of, you can merge them together. Okay, such that, and the key point is that such that this term, this expression is going to give you 0, right? When right? When it's 0, then everything is 0, okay? And 1, yes? Right? Which implies, so there's only 2 possible states when the state is in agreement with itself. So I'm a cat node. When I see a cat, on average, the expectation AIK, here is AIK expression, okay, is equals to, what's the expectation of AIK? Or this expression rather. It's either 1 or 0. On average, it's going to be, yeah, 0, half, 0.5. It's weird. It's binary, but mathematically, the expectation is half. Critically, greater than 0. As opposed to the other case where the average is 0, here the average is going to be non-zero and positive. Okay? And it's exactly half in this case because it's binary. So imagine if it's not binary, right? Then it wouldn't be 0.5, but it would be some positive number. Okay? Got it? Okay. Right, so, but this is just only the expectation of the input responses when the states are the same, the external states are the same. That is not yet exactly what we want. Exactly what we want is to do with ASJ, okay? So we need to get from here to the expectation of AS, all the states of J. So this is the expectation for AIK, but the full expression is like this. So we have to do a little bit more work. When the states are the same, for the full expression of the sum, this one, okay, the sum of over k of the 2AIK, AIK minus AIK, this is really redundant, but the expectation of this expression, okay, is going to be equals to the number of, because of k nodes now, right? You have to sum over all the k. Just as what we did is the sum over all, where were we? Yeah, well, sum of over all the possible states, okay? So we have now the sum over all the possible nodes, all right, is going to be n of k times 0.5. because it's a n-bit word. So if you have 3 nodes, then the average activity of these 3 nodes will be 3 times 0.5. If you sum all of the expectation of the sum of all the k nodes, right? That's what this will be, right? So the expectation will be nk times 0.5. If you have 16 nodes, then it will be 8. Okay? Which implies, and again, we are still not there because this is still just about the AI and the AI. What we want is AJ, right? So how do we do that? The expectation of AJ, remember, is equals to the over J of Wij AI, right? Which is therefore equals to 2aj minus 1 times nk 0.5. What it is plugging in this 2aj minus 1 from the 2 pages ago, where we put 2 into 1, right? That trick, right? This expression, we put it into here, so we can re-expand that here, and we get, since we know that this expression is nk 0.5, therefore the expectation of aj is going to be 2aj minus 1 times nk 0.5. Okay, we take those equations and we put it here. In other words, it's greater than 0. Okay? So that we have now shown that if I am encoding not cat, all my activity on average, no matter what, sometimes I'm high or low, on average I'm going to be 0 if it's not cat. But if I like cat, I remember cat, if in my memory I like cat, and I see a cat, my average response is going to be not 0, greater than 0. So this is his way of proving autoencode, right? I don't remember cat, then I don't respond to it. I remember cat, I like cat. So if you ask me about cat, I'm going to respond to it on average. That's it. Okay? So this is a kind of proof way of doing it. Okay? Any questions about this? Okay, it's good to exercise your brain a little bit with this math, because when we go to the backprop, you will see that backprop has a different goal. And I guess here is to reiterate, right? It has done it, right? If that memory, that input is not me, then I am not going to activate. If the input is me, then I will activate. So in this proof, he has demonstrated that AJ can be made to be equals to AI according to these 2 operations in place, okay? If that's the goal here. Backprop's goal is different. Backprop is not going to be about making input equals to output. In fact, backprop is supposed to be learning how to make any input into any output, okay? That's very different from saying that the output must be equal to the input, correct? Okay, so appreciate this kind of mathematical exercise, because then you see how they think and then get to where we are at, all right? All right, so this is the proof of the Hopfield, why Hopfield does autoencode in this way. One final formula or a mathematical thing is that we also have to evaluate the model, and this will come in today, later, when we try things out. Evaluate the model, And to evaluate the model, let E, in this case the E is not expectation, this is energy. Okay, what we mean by energy? Well, E is equals to minus half, okay, summation over K and R, and remember where K is not equal to R, where K equals to R, then it's going to be 0. Wij is going to be 0, okay. Ik, let me expand this out. JR, AIK, AJR, and this is going to be the energy, total energy of the system. Does this equation look familiar to you? Maybe some. Anyone did physics? Right? So, 这是什么 energy? Okay, 动态 kinetic. Okay, kinetic. Okay, why is this profound idea here? If you want to quantify the performance of the model, okay, if you want to evaluate the model, one metric is how kinetic this model is. Okay, in other words, is it very stable? It doesn't move, so it's reached its lowest, doesn't move anymore, so it's 0, or is it still moving? Kinetic, 还在动, right? So in other words, if you capture whether this model still has some motion in it using this expression, means it's not yet reached its most stable point, right? 因为 like total energy, right? 对吗? Right? So it's either a moving part or the non-moving part. And if it is still moving, then there's still not yet stable, it has not reached yet its stable part. But if it has made it such that its kinetic component is 0, then whatever is left is the potential. And that part is the stable part, right? Okay? Until something else does something to it, then it changes its architecture, it changes its state again. So this concept comes from physics, okay? But the idea here, therefore, you are saying that, yeah, this is the velocity, right? Because it's the activity that's changing. And this is the mass part, right? The part that is part of its architecture. And if you quantify how the activity is changing with respect to the architecture, you quantify whether this is kind of reached a stable point or if it still has some space for dynamism, okay? To show that we do a little bit of calculus, okay? With respect to, its output states, so its kinetic energy, okay, with respect to its output states, okay, whether its output states, as its output states are all the possible different output states it can get, the kinetic energy is going to be equals to the half is going to drop out, right? And then just this part is left, right? You just take away the half when you differentiate according to AJ. So the AJ part is cut out, and the half is dropped out, and you get this part. The critical thing for this expression is that it is negative. This implies that energy change in energy is less than 0 as AJ changes. this is a loss function, and this will come it's kind of like a gradient descent. It's always going to reduce. This is yet another proof. If you have kind of this sort of setup where you have the input weights and the input states and the output states and the mass of the network, or the weights of the network, how these and you set it up such that it is a negative half, all right, in the form of a kinetic function, it's just going to be negative. You will ask, well, it's because he imposed a minus half there. There's nothing special about this. Yes, all right, but it doesn't have to work that way. You have to see, this is kind of like, we expect the energy to behave like this, that it can only go lower and lower, right? Let's see how it works when we try out. You will see, it really does only go lower and lower, all right? But this is one way to evaluate whether this loss function is implemented, all right? So this is one way to evaluate. This is one way. Another way that we will be using is what is known as the Hamming distance. And this is very simple. Hamming distance, which we call h for now, okay? Although h stands for many, many other things. The Hamming distance is simply the AIK minus the sum of the AIK minus AJR. And since the number of k is equal to the number of r, so this will work. Okay, as a vector sum, it works. Okay, you can subtract it. Yes. Okay, so you can see how the Hamming distance works is that if I have encode Aj equals to Ai, right? Then my Hamming distance will be 0, correct? But to the extent that I never successfully auto-encode, my Hamming distance will be greater than 0. Okay, sorry, I should say it should be the modular, absolute. Okay, it doesn't matter whether it's higher or lower, as long as it is not the same. Okay, yeah. Okay, so these are the mathematics we want to finish up, and then now we want to move towards the model. And so this is a good time to take a short break, and then we come back to the Google Colab to demo the model for you. Okay, any questions? How is this compared to the online YouTube? Is it helpful? Is it confusing? Is it unnecessary? What do you think? One day you'll get it.
I need more time to process.
You need more time, yeah. Yeah, so did I. I needed more time. I need a lot of time. I read the paper over and over and over again. And yeah, it took quite a while. I certainly didn't get it when I was learning this course. I got it after. Yeah. But do the YouTube clips, I have not seen the YouTube clips. I have not seen any YouTube clips. I've seen YouTube clips to give you the gist of the autoencoder or the Hopfield network. I have not seen any YouTube clips talk about the proof of it, at least not from the Hopfield's own paper. Yeah. So this is the part which I don't think you can get this from the YouTube clips. Okay. Well, of course, our video we put it on YouTube, but I'm talking about other YouTube clips. Okay. So I find that if you want to if you are interested and you want to get into this, my advice is this is a good exercise from the perspective of, as we talked about over and over again, engineering approach is I have a tool, I have a set of tools, I use it, I don't really worry about how it works. I mean, I might care, but not the priority. The priority is whether it works or not and how I evaluate it, right? Here, we are interested in why it works, and a lot of why it works is mathematical, unfortunately, right? And although in this class, we don't demand that you worry about the mathematics, so I show you this, but I don't ask you any of this in the assignments. I feel like the spirit of this course is you kind of have to appreciate the beauty of the mathematics, right? If you see that it's all just matrices and arrays, and products of vectors and matrices, right, are really just transformations and expressing the vector, rotating it, or projecting it in another space and all that. This is really what the neural network is doing. It's taking the input arrays, dot product it with its own arrays, and giving you another array. And this is just transforming things one way or another. And somehow, some transformations, like this one, with these equations, and they are nonlinear ones, right? Because Agarwal argues that if it is linear, then you might as well just do regression, right? The beauty of the neural network is nonlinear, and therefore, we cannot easily prove. So this proof doesn't give you the answer. It just gives you why the answer will work, right? So you still have to play out to get the answer, okay? A linear one, you don't have to play out. You can absolutely derive the answer, right? You know how the answer works, you also can derive the answer. A nonlinear one, you have some guarantee that it will work that way, but the answer still has to be played out, simulated out, okay? So this is where the mathematics comes in to help you to understand why this neural network, if you use these functions like that, and you see their mathematical relations, that you will arrive at certain qualities of results. That, for example, you don't respond to non-common states, and you respond to common states on average with a scale of 0.5, right, in a binary world. And also that if you think about this as in terms of energy, if you couch it like this, and you see how you can then evaluate whether it has changes in its kinetic states, or has it reached kind of like a minimum kinetic state. And if you see that because it's a negative, if you put it as a negative, you can make it or use it as a loss function. In other words, you can use it as a way to say, I'm satisfied with this model's training. To me, it has reached some minimum. It doesn't look like it's going to change any further, so I can stop the training. So that's what the loss function will help you. And so if you appreciate all of this, when we go to the back prop, it becomes automatic, because then your thinking has been fixed that first I start with my goal. Here the goal is make AJ equals AI. Then I see how my equations, if I mess around with it, will fulfill my goal. So here the equations are the binary ReLU and the Hebbian learning rule. Okay? And then I see how if I have a loss function using these elements, I will have some sort of a way to test and evaluate the model. So if you go to backprop, it'll be the same thing. I have a goal, I have some equations for the backprop, which is a multi-layer perceptron, and I have some loss functions to evaluate it. This will repeat over and over again. You'll see that coming up. So the beauty of the mathematics will be the sort of the unique or the value here of this perspective, okay? As opposed to just engineering using it, which is important, but here we focus on this aspect of it. Okay? All right, then in that case, let's take a break from all this math and like brain headache. Take about maybe 10 minutes. So let's come back at 10:30. Let's just say 10:30, we come back, and then we'll switch to the collab. And again, let me reiterate, from here on, I'm done sort of lecturing the Hopfield network thing, and it's kind of, I'm going to push it over to you guys for the practical aspects. So for the next half, I'm going to show you the collab. next week, you will come in and you'll be working by us, and I will help you with your code, all right? And the videos are online, okay? I will be releasing assignment 1, and I will go through a little bit of it with you. And so that next week you come into class, you can continue working on assignment 1 or any other problems, and it will be practical, more practical than anything, okay? So that's how the model is going to be for now the next 3 models, Hopfield, the backprop, and the unsupervised learning. Okay, so let's take a break, and we'll come back at 10:30. Okay, let's continue. 有什么问题吗 ？Any questions? Yeah. About the proofs or something else? Huh? Yeah. Which one? This one? Okay. Yeah.对，这边是 AJ，yes。这个，对，这是 AI，对。不知道为什么。Okay, because here at first we are not talking yet about AJ. So here, so this one 这个应该 OK 吧哈 ，right? Because 这个就是 if you put this in, you get 这个 component which is this second part the component, right? 它 expectation 是 zero, right? 那如果因为 ASISJR is proportional to 这个整体 ，so if 这边 expectation 是 zero，therefore 这边 expectation 也是 zero，right？Therefore 这个 expectation of AJ， 因为这个是 AJ 了，是 zero，so 这个 AJ 这个 OK 吗？这个 AJ 等于 zero OK 吗？哈？可以吗？应该可以。这是因为这一部分 expectation 是 zero，right？ 可是记得 AJ 等于这个整体 ，right？ 那如果这部分 expectation 是 zero， 那 AJ expectation 也是 zero 啊 ，right？OK， 这个 OK。So that's why 这边这个是 zero，then 这边直接跳到 AJ 是 zero， 因为这个是这边 ，right？And then 这个是这边。好，所以这边的 AJ 是这样子的，可以吗 ？Okay. So similarly， 这边 AIK 这边 expectation 是0.5，是针对这边的部分，是这个是0.5，这个 expected value of AIK 是0.5。Right? So the expected value of 这个整体是 nk 乘0.5，因为有这个 sum of k 的这个部分要处理，可以吗？好，所以这个 AIK expectation 是针对一个 AIK 的程度先 ，that level 先，然后 if AIK expectation is 0.5，then 这个整个 expression 的 expectation 是 nk 0.5。可以吗？所以这个 expectation 0.5，then therefore 这个 expectation 是 nk 0.5，可以吗？啊，那啊，第二行这个。对，这个就是这个啊，这边啊一样啊 ，nothing different. I just put this here 啊，这是一模一样的 equation from here。我只是说，这个是一个 trick， 所以这就是为什么我心里有一些矛盾 ，because 他做的是 ，there is no reason why you want to separate these two effectively，OK？、可是他是在用 let's imagine 先。Let's do a trick to think like, what if 有这两种情况 ，OK？So 他先，因为会 put prime here 也可以啊，或者是 prime there。总而言之，就是要把它两个 ASI 的这个部分分开先 ，OK？ 假设外界的 ASI 跟我现在的 ASI 是长得我喜欢的 ASI 是什么 ，right？So 这个 expression 跟 这边的 expression 是一样的 ，OK， 只是说 in this page we first consider when 它这个 prime 是不一样，这个 prime 的意思是这个 ASI 是针对外界的刺激 ，in the situation where 那个刺激不是我这个 node 喜欢的，不是我这个 node 记得的，可以吗 ？OK， 所以这个是一个 case one，OK， 可是这个是 case two 了 ，case two 就是说一样的 expression，OK， 可是 let's imagine that for now 现在的资讯是我这个 node 我喜欢我记得的，那这样子一般来说我的反应会是怎么样 ？So this is 对于我不记得的东西，我一般来说我的反应是什么？我的 input 的那个 state 是什么？然后这个 case two 是对于我记得的东西，我本来就 encode 里面的东西，我对于它的反应是什么 ？Then 如果我的反应是一部分是平均来说我的反应是0 ，then 我的 output state 平均就会是0，因为这个 equation 在这个 state。可是如果这边我的一般来说我的反应是0.5。Then 平均来说，整体来说，我的整个系统的反应是 nk 0.5，以及也就是说，我的 output 的话的反应会是 2aj 减1，这个其实不太重要，重点是它是跟 nk 0.5有关，那它是大于0这样子，这是它的那个reasoning。那意思就是，而且其实这个号码不太重要，这个重点是不是0，它而且是大于0，相对这个是0。So that is the auto-encoding part。我记得的时候，跟当我面对到我记得的东西，我的反应会是不是0？当我面对到一个我不记得的东西，我的反应是不是是0？一般来说 ，So 回到一个硬碟 ，right？ When I want to match 一个 string, if it is not match, give me 0, right? Not match. If it is match, give me not 0. 就是这个意思。That is the auto-encoding part， 对不对？就是 I give you the item that you are the content. So on average, my activity will be matching the content that I am supposed to remember. But I will be giving you 0 if the content is on average is not matching the content that I'm supposed to remember. 这两个步骤。So 这边这个 form 是跟这个一样的，只是前面的是 case one when 那个 state 是不等于。Then in this case 这一页的是 then let's switch and imagine 那个 state 等于我应该要记得的。In both cases， 我的 average 的这个 expression， 一个是0，一个是不是0，一个是大于0 ，right？ And if 我的 input state 一个是0，一个不是0 ，then 我的 output state 那个0呢就会维持是0 ，but then 我的 output state 会是跟着 input state 不是0这样子有关，这样子。So that's why only later on, then we have the AJ part, just like here the AJ part. So it's always from the input first, and then the input expression, and then from input expression we remember that the input expression is related to the output by the equation. So then the output can also be derived from there. 这样子有帮助吗？还是要想？我也想了蛮久。That's why I say the notation is important， 就是哪一个是 J 或 A、I 或什么，这个是重要的。还有，没事。 if you still have the, so as I said, this is just a proof from the mathematical point of view. Struggle with it, 这个是很好的事情。I think, but it is not necessary for the assignment， 这样子 ，OK。But I mean， 人家就是在他 paper 就做了，然后有 Nobel Prize， 所以应该是 OK 啊。Right, yeah. 可以吗？有比较好 ，OK。I found what helped me was I went back and I wrote out on paper 那个 array， 然后那个 element 就有一点点 ，like I went back to do this, like in Excel. I made this array and I put numbers in there. I really put numbers in there, and they can only be 1 or 0, right? And then I read as in 我 implement 这些流程 and I let the numbers and let it have real number. And then I see, 真的是expected. 就是 expected 就是你知道怎么算嘛 ？It's the average of all the possible situations. So actually play out in Excel 这样子 for example, or whatever code you want. Then not only you know the mathematical, you know that if you play out, it actually is going to be something like that 这样子 ，OK， yeah， 可以哈。I mean, you probably still have some uncertainty and all that. I completely understand, and I think it's good to still struggle with it. Don't worry, if you need time, if you still have questions, let's say next week, or even offline, again, can ask me anytime. All right. Okay, let's worry more about the practical part. I think that's more important for this course in general. And that is how to actually make your own neural network, and in accordance to the psychological process that we want to model. Okay, in this case, content addressable memory or memory. Okay, and or our biological style of memory, and then how to evaluate it. Because in the evaluation, you can also do expansion. So maybe not just in this course. If you make a model here in this course, there's nothing stopping you from expanding your model to really using it in your own work outside of this course, as you will see. Okay? And I'm going to do it from the perspective of an assignment, your assignment, which is assignment 1. So if you go to the NTU Cool, next week is assignment 1 start, okay? So, but I will open it. Is it open already? I don't know if it's open yet. Can y'all see it? Can, okay. So good, so you can see this, and then you can start working at it. I think the due date, I usually will set it like, just before the next assignment, right? So assignment 1 will be due on the day assignment 2 is open, okay? But you can see it, and we will use it to not only do the assignment for the coursework, but as to help us, and that's the point of the assignment, to help us understand how this neural networks work. Okay, so from the perspective of the assignment, I will use this, and then I have also the Google Colab, which is working through the first part of the assignment. Okay, so we will go through that sort of back and forth for the next half of this class today. Next week, it will be lab time. You can continue to work at it, and I will be here, and then I will maybe have you guys show your work up to that point. You wouldn't have completed it yet, unless you have 很厉害就做完. But then you can show your work, and then we can have interchange with everyone. See, some people may be struggling, have questions, or some people have answers, and you can share, we can discuss. Like, hey, is it working? What are some issues? Do we really believe Hopfield? Or do we think that, no, it's all crap, or whatever? Everything's fine, all right? So it'll be open for next week. So, but let me show you how to work through the format, because I think really what you guys need is the format, and then you can implement it. So a good way to understand that is through the assignment. So let's see assignment 1, which is about the attractor model, okay? And disclaimer, this is adapted from when I did my neural networks course in UIUC. And I expanded it more and I shaped it so that it's a bit more digestible. When we got it, our goal was, the way they do it is, they give us the assignment and it's just a few lines of maybe the first few questions, first few lines here, not the whole thing here, just a few of the parts of this assignment. And then in UIUC, they do it this way. If you are undergrad or master student, you just do the assignment part. If you are a PhD student, you do the assignment part, plus you have to write a paper about it. Something like that, okay? And so we wrote a paper about it, and this is our unpublished paper, right? So you can see this is my paper on the Hopfield network, okay? And you see it, it's like that, right? And then it's a full-blown simulation paper with background, hypotheses, methods of the simulation, and the actual results. And we have figures and proofs and all that kind of stuff, okay? So this is how we learned it back then. Don't worry, I'm not asking you to write a paper. I think, if you are a PhD and you want to do it, you're very welcome to do it. But at least for this class, I would say just follow this assignment is actually pretty good enough already. Okay, so first question is to build your own binary autoencoder, which in this course we know as the Hopfield network, using whatever environment you want. I'm going to use Colab. Implement it as a 16-unit autoencoder using threshold theta 0, so theta equals 0, and a settling criterion of 30 iterations. I will tell you more about this. That is, if the state of activation remains unchanged for 30 iterations. You will see that in the implementation, the network will be flip-flopping for a bit. Its activation state. So as you said, on average, the activity of a unit is going to be 0 when it is when the stimuli are not, the stimuli that this unit remembers. Okay, this unit, not this network. Okay, this unit remembers some aspect of the external world. It remembers something about the external world. On average, if the external world is not what it is supposed to remember, on average its activity, sometimes it's on, sometimes it's off. Sometimes it's on, sometimes it's off. So that's the activity change over many iterations. But on average, if it is not something it really remembers, on average its activity will be 0. Okay? On the other hand, if it is something that it remembers, then on average its activity will be not 0. Okay? So this is, when you implement, you will see. There will be some flip-flopping, and it generally will settle, but we give it 30 iterations, flip-flop like 30 times, until we realize it doesn't change anymore. Means it must have come to some conclusion. Okay? You will see how that works in real life. And usually we use the Hamming distance. Remember, the Hamming distance, as long as it is greater than 0, it means that the state is not the same as the previous state, right? That the state is something changed, right? So as long as it's changing, not 0, the Hamming distance is not 0, then you still keep doing it until Hamming distance becomes 0, or you reach 30 times. The Hamming distance never reached 0, but it's already 30 times already. You stop. Okay? So this is what this first part means. Now, it really only makes sense if you integrate this first part, 1a, with part 2. So you want to train a network on these following patterns. You will note there are 4 patterns. So 4 states. You can imagine it as cat, dog, mouse, tree. Okay? So the first one may be cat. Cat means, and it's 16 units, right? You count 16-bit word. So let's say cat has 16 features to encode it. And then these other 16 features, if you change it, then it is dog. And this, if you change it some more, then it is mouse. And if you change it some more, it is tree, or something like that. Okay? Of course, you can encode some more things, but for now, for this exercise, let's just keep it to these 4 patterns. You will also note these 4 patterns are completely orthogonal to each other. These are called Walsh functions. Walsh, W-A-L-S-H. Okay, they are orthogonal to each other. Okay, right? You see. Right, you can see how they are orthogonal. Okay, it's like it's exactly always alternative in the ones and the 0 patterns. Okay, in other words, these 4 patterns are not linearly derivable from each other. Right, learning one pattern will not tell you anything about the other patterns. Okay, so these are Walsh patterns or Walsh functions. All right, so I'm going to clear this. And in the above and subsequent vectors, one refers to, I have to clarify this, one refers to active units, ASIK equals 1. 0 refers to ASIK equals 0. Okay? So let's try this part, 1 and 2 together. And how do I do that? Okay, so in my collab, and I think you guys can access that as well, right? Okay, in my collab, I start off again with some theory, all right? But, and you can read through, but you'll be familiar. Basically, the problem is, so in implementing any of these neural network models, this is the framework of the manuscript or the study that I suggest to you to help you organize your thoughts so you know how to approach the problem. First thing is, define the problem, okay? As we did in the perceptron, it is about understanding the psychological principle we want to model and formalizing it, converting it into a hypothesis, a formal hypothesis, and the corresponding data table. These go hand in hand. So the idea here, the psychological goal here, you can read through, okay? But it is about instantiating content addressable memory in silico, in a machine, okay? And there's more details here about content versus index memory, all right? Yep, just to highlight again, this is the Nobel Prize winning work, okay? All right, so from that, that's what we want to do psychologically. How do we do that in a formal sense and in a data table sense? Well, a data table that will do that will be a good data table that we can use to do that will be the Walsh functions. And this is exactly the assignment ones, right? And so what is the formal problem? The formal expression of the problem means if we have 4 Walsh functions like this, the goal is to make, and this is AI, right? Remember, it's the ASIK, right? Is 1, ASIK 0. So these are all the universe of AIs that we can possibly have for this network. The goal is to make AJ equals to AI. So this is the data table. The data table is that we have an input like this, and through some retrieval process later on, we want the output to be like this. This is the data table. Okay? Very simple, right? Nothing controversial or too big a leap here, really. All right? So this is the, in one shot, right? So easy. That's why this is Hopfield is the first one, because as a theoretical, conceptual concept to the formal, the leap is not that far. It's actually quite okay. All right? So that's our goal. This is the data table. Okay? Similar to the perceptron. You want a logic gate, the AND/OR logic gate or the XOR logic gate. That's your data table. Okay, so we have this data table and we want some sort of a network that does retrieval, that after we train it, it can do retrieval to give us this kind of output, right? So let's visualize the above first. This is not so necessary, okay? But, I think it gives you some ways of working with your data. Again, I use the prompt in the AI mode for my Colab, but you can use it any other way you want, or you can write your own code. And my prompt was, I want to plot binary vectors as rows of black and white heat maps, okay? So this is, excuse me, this is the library, matplotlib, to plot things, and numpy, which is the NumberPy, which is the array library in Python, okay? And it creates a function so that you can plot binary vectors as heat maps, okay? And heat maps are arrays, and the color, the intensity, which is the heat level, means something about the number that represents that location. And so if you run this through, I have a function. This part here defines the function, which takes in the binary vectors as input. So whatever is here, right, it will take the binary vector, which is a string of ones and zeros, and then it will convert them into a plot, which is the matplotlib, and using the heat map gray. I like use gray because actually using any fancy colors is meaningless because this is a binary world. So it's either 0 to 1. There's no other, red, blue, green channel here to worry about. So just use gray, simple, it's good. But feel free to be fancy if you want to use other colors, okay? But then there is some, formatting to do here, but essentially the plot is the key function. So if I feed this function the binary vectors above, these binary vectors, it will plot them out as a heat map, like this. So let's make my binary vectors these Walsh functions. So let's make binary vector equals to the Walsh functions in the data table, and print Walsh functions, and run that function above, the definition above, giving it this binary vector as the input, right? And the result will be this one. So sometimes this kind of highlights something, and I want you to exercise this in your assignment answers. You can give me numbers. You can give me these vector array numbers. Which one is easier to see? The figure, right? You can give me all a whole array of numbers, and I'm like, oh, I have to see every one, every zero, right? But you give me one figure, one shot, I know, oh, Walsh functions, because they are all orthogonal. Okay? All right? This is something to value when you are doing your modeling, not for so much also for reporting to your professor or other people, but even for yourself. When you do something, right, try to see if you can visualize it. Even with statistics, we know, right? You run some correlation and then some R value it gives you. But nothing beats you plot the scatter plot, and then you see something that beyond just the R value, right? And you also understand why the R value is there, okay? So visualization is key. So whenever you can, plot things out, visualize it, so you feel confident about your data or the numbers that you are working with. Okay, so this is the input that we want. What this means is we want our model to be like, see the first row, so that when I give you the first row, you can say, I recognize, yes, that's something I learned before. And then the second row, okay, see the second row, and then, yes, that's something I remember before, okay, and so on and so forth. Now, this is the hypothesis given the data table that if we set up a Hopfield network, it can exhibit content addressable memory as we experience psychologically. And how do we claim or conclude that a system has content addressable memory? A test. We do a test, and we design our tests stringently because by necessity, content addressable memory in a system means that this system can retrieve the full trace based on partial input. That is the definition of content addressable. you can find this person by just giving me the address of the person. You can find the whole house just by giving me one line of the address, right? That's content addressable, okay? So you don't give me the whole house. You give me part of the house. You give me an address part of the house. I can find the house. So you don't need to give me the whole cat. You give me something, part of the cat, I can retrieve the whole rest of the cat for you. So you don't need to give me the whole wash function. You give me a part of it, some key parts of it, and I can retrieve for you the whole wash function. That is the test of content addressable memory. Okay? So formalizing it means I have this data input, I make a network, and if I give the network some part of the original data, the network can return to me the original data table. Okay? So the aim here is to make a 16-unit Hopfield network that retrieves all function, which is essentially this question 1 and 2. Okay? So how do we do that? Simulation 1, we run the simulation, and we say we want to implement a Hopfield network. And again, we want to visualize the architecture. It is a 16-bit word that the data table consists of 16-bit words that we want to encode and retrieve. So the network must have 16 nodes. In other words, it is a 16-node graph where every node is connected to every other node except itself. So remember, this is essentially like 16 of the nodes, and it is connected to every other node. Okay? But this I equals j, w equals 0 here. No, let me express it correctly. Okay? Essentially what this means is I want a 16-node network like this. Everything is connected to everything else except itself. As an array, okay, this is AJ, this is AJR, right? All here will be zeros. This is the Wij array. Everything else off diagonal has some non-zero value, but or it could be 0, but there's no hard rule about that. There's some learning. But on the diagonal where I is equals to j, the weights are set to 0. Means the network is not connected to itself. It is connected to every other node in the network. Okay? Okay, so that's just to visualize it. I tell the AI to give me a code that will plot a 16-node graph. I say graph because a graph consists of nodes and edges, which is a neural network, okay? Such that this graph has every node connected to every node, other node except itself. And the tools that it gives me are matplotlib and networkx. Yeah, this is sort of cheating. This is a toolbox for neural networks, but I'm just using this for visualization. I'm not using it to do any computation, okay? So if you want, you can spend time to look through this code, but essentially if you run it, it will do 16 because I want it to do 16 nodes, right? It will do 16 instances of nodes, and these nodes will be connected to every other node. Oh, wow, so big. How to zoom out? Let's see, can I zoom out? Here, I can't. So I'm going to just do this just to show you. Okay, this is what this, for the wash functions in the assignment, your Hopfield network essentially visualized looks like this. Okay, pretty cool. All right, 16 nodes. Every node is connected to every other node, but not itself. Just to visualize. Nothing mathematical happened here, just some fancy eye candy, that's all. Okay? But it is helpful, right, to visualize this because again, if you go to other networks, backprop or whatever, it will look different, okay? And how it looks represents how it's connected, and how it's connected will change its function, obviously. Okay, so let's go back to the code, the more important part now, okay? So we set up the simulation materials and procedures. So first, import some key libraries. Obviously, we need the NumPy array, and we need some plotting tools, all right? I used to have some plot style, but I think this was made decrepit, so they don't use it anymore. So I've commented it out, all right? But it's just a style thing for the plots. It's not important. Okay, so the first thing we need to do, so here's the key, the dirty part, okay? We need to define how the Hopfield network learns. We already know the Hopfield network is an array where you have that W array that I just drew. It's an array where everything off diagonal has things, but on the diagonal is 0. But how do we change the values in this array? It is by the Hebbian learning rule, which is this one, okay? So this is a function. I have put some comments here, but what this is essentially is, I have a function called, I want to train the Hopfield net. This training function will take in some original or initial W set of weights or array, and some input stimuli, vector of stimuli activity. I will initialize the weights here. If the weights, the size is 1, then I will make, meaning that there is nothing yet, okay? Then I will make the weights equals to a whole array of 1s. Okay, that is the size of 16. Because NP shape A is going to give me 16 because it's going to be a 16-word vector. Okay, 16 by 16 array of 1s. So at first, W is, if I put W as 1, then 1 times an array of 1 gives me an array of 1s. Why do I do it this way? Because, as you will see later, the W may not be just number 1. It may be already a trained network, which itself is 16 by 16, in which case it will skip these few lines, right? Because W then size will not be equals to 1. It will be equals to 16 by 16, okay? And in this, so it will not set W to be an array of 1s. It will set it to, it will use whatever trained array of W's that it has, okay? But in the initial state, nothing's been trained yet. So I just want to run an initial network. I just set W to 1, and it will first instantiate according to the size of the input A, 16 by 16, in this case, array of 1s. Then I will begin the training. For every state that is in the shape of a one vector, sorry, this is shape of a one dimension, okay? A can be many, many states. So for every state that is in A, do the 2A minus 1 delta W, okay, in this case, the change, okay, in W is equals to the outer product of the 2A minus 1 transpose 2A minus 1. Okay? That is the Hebbian learning rule. All right? And in which I make the input equals to the output. And then I update the weights. The weights is equals to whatever was the original W plus the amount of change that I have to do. Okay? And then 0 the units that are not auto-connected, right? When I equals J, make the weight 0. So that's what this line does. Okay? And then return the W. So I have, for S is in range of the A, okay? So let's say A is like this. A is like this. A has 4 states, okay? 16 units, but 4 states. So S will be state 0 to 3, or 1 to 4, okay? So this will repeat 4 times. So imagine 4 times. when A is 0 and A is 0, it will be 0. When A is 0 and A is 1, it will be 0. 0, 1, right? And then 0, 0, it will be 1, right? So according to the Hebbian learning rule, remember? Okay? So all these like commonalities will be encoded into the dW, and the dW will be encoded into the W. The W will accumulate all the dWs. And eventually, after one round, this is one epoch, one iteration, okay, of training the 4 states. It will stop after training 4 states one time and give you, okay, this is the first time I've trained 4 states in the W. This is the resulting W. This is one iteration. Okay, now, so, okay, this is the learning rule. This is the training critical part, the Hebbian rule. Any questions? So we have this function, all right, and then we will use it later. So we haven't actually done anything yet. We just define this function first. Okay, next we have to define the autoencoder testing, and here is where the activation function comes about. That okay, I have these weights that are trained, but these weights will lead to some activation state subsequently, right? According to the binary ReLU function. So this is going to do the test net. I'm going to test Hopfield such that the output state, right, is going to be a binary ReLU of the weights and the input state at a particular time. Okay, that's why the test net has the weights that you trained, the input test vector that you want, and the number of times you want it to reach some settling point. Okay, some time concept here. So what is this function? I have to initialize some parameters, and by the way, I'm implementing this as is described in the Hopfield paper. Hopfield himself describes these parameters. So if you look at his papers, he does have all this. Activation threshold, energy start vector, blah, blah, blah. He may not say it this way, but he has these components in there, okay? But I initialize that my theta, or in this case I call it U, is 0, according to the assignment. Threshold is 0, okay? I don't want to use T because I already used T for iteration, so I use U as the threshold, okay? So just bear that discrepancy. I also have a evaluating vector, the energy, and the energy starts at 0, and this is the kinetic energy that will later on you will see it evolve. I also have the Hamming distance. At first, I say the Hamming distance starts at 0, and we see how it goes. And the consecutive no Hamming distance change counter. I start at 1 because I want to count how many times does the Hamming distance change, and if the Hamming distance change more than 30, stop, right? And the round counter and all these are other counters, and fail, these are more like operation contingency I put in. You will see how they come into play, all right? So how do we try this out? Very cool. So we first have a while the consecutive counter is less than the threshold. So the threshold time that we want is 30 iterations, right? If we reach 30 trials, epochs, we want to stop. So as long as the S is less than or equals to 30, we can run. Once it's greater than 30, we stop, okay? We create first a buffer, okay? A temp equals buffer, A copy. And then we randomly select one unit, so asynchronous, okay? What this means, I have a 16-bit word. I want, and this is the input word, I want it to give me the output state. So let's say whatever stimuli you give me, let's say you give me a 16-bit word. Let's say this is my probe. So let's say I train you on cat, dog, mouse, tree. Now I give you this new information. Can you tell me, is it a cat, dog, mouse, or tree? Do you remember cat, dog, mouse, or tree? Given that this new state of info is a partial cat or a partial dog, do you think it's a cat, dog, mouse, or tree according to your memory, right? Now, nowadays, the Hopfield, they might implement it differently, but in the original paper, John Hopfield says, to do this kind of testing the network, what would the network return if I give it this input? Well, the network, Hopfield says that we should do it this way. Which color should I use? Maybe blue? Blue, okay. Randomly select one unit at a time, okay? And then update the unit, okay? All other units, not itself, will be equals to the binary ReLU function, the f being the binary ReLU function of all the weights, okay, except itself. From the input, okay, update this weight here so that if this is greater than u, which is the threshold, implies that it is 1, else it will be 0 for this unit. Okay, so select this unit to operate on asynchronously. So select one unit, see all the other units' activity and the weights that you have right now, and then update only this one unit, this one time. Okay? So that's what this is doing here. See, a temp I, so select unit I randomly, okay? Then make a temp I equals to the binary ReLU of all other things according to the threshold U, okay? All right, so that's the way Hopfield does it. You got this? I'm going to wipe it out. Okay, yeah? Excuse me. Then I get all these are redundant. These are the old way of doing it. This is, you see, I can implement it in one line with the max sign function, or I can do the if-else way. This way is very inefficient, too many lines, so you can do it in one line. All right, so I commented it out. Okay, so just do one updating. Okay, remember we are in still just one epoch. Okay, so just select randomly one, update it, then calculate the energy, which is -half of WAA. Okay, that's what this is. This expression does. Okay, and also calculate the Hamming distance, which is the updated A temp minus the original probe partial cat stimuli that you want. All right, and this is the sum of the absolute of the differences between the two vectors. Okay. If HD has changed, meaning HD is not the same as the previous one, then increment the counter, the HD counter. Else, if run is less than 1,000, keep the counter as 1. Means if not changed, then just keep the counter as it hasn't changed yet. Okay? I put this R as another flag, meaning that it is possible that it is never changing, but it still never hit 30, or it keeps changing, but it still never hit 30. Anything like that. I don't want my computer to burn and to keep running infinitely, because whenever you use a while here, you have to be very careful. You never know when the while will run infinitely, right? So you always want to have a fail-safe within our engineering constraint. This is the fail-safe. That no matter what, however I want to do my code, I can have my iteration is 30 or whatever, but I will always want to have a fail-safe that I don't want to burn my chip. So 1,000 is as much as I will tolerate. You can do 10,000, you can do 1 million, it'll be okay. But this model will perform pretty well. So within 1,000, it will never hit that. You can be guaranteed within the assignments, it shouldn't be running for a whole day. If you are running your code and it's running for a whole day for the assignment, your code is wrong. Okay? I was running this like in an old tiny iMac like 20 years ago, and it did it like within, a few seconds, a few minutes max. Okay? So if you're running like a whole day and you still haven't settled, something's wrong with your code. So that's what I mean here. You have to put a fail-safe here. And so then else flag to fail settle after 1,000 runs, then just quit and say fail. Something happened, so I have to do troubleshooting again. So that's why I have the additional parameters. Okay, this is just some coding tricks. So just so you know. But otherwise, if it is running healthily, then this S will be updated incrementally, and then update the run counter accordingly, and copy the ATEM. Now, I have to do this, that make A equals the ATEM copy, because you know how Python works. For those of you familiar working with MATLAB or R, if you make A equals B, right, in MATLAB, A will become a separate thing and B is a separate thing, right? In Python, if you say A equals B, A is just a shortcut to B. So if you change A, B will change also. In MATLAB, if you say A equals B and if you change A, B doesn't change, correct? In Python, if you say A equals B, then literally A equals to B. That if you change A means you change B. That's how Python thinks of it. So in order for you to make A is the same as B, not that A equals B, you'd have to do A equals to B dot copy it into A. So that now A is another thing that starts off with the same state as B, but if you change A from here, it won't affect B. That's what this means. Okay? Those of you familiar with Python, probably this is nothing to you, but for me this is a big problem because I come from a MATLAB world. And I was like, why I changed A and then everything else was changed? I was like, I couldn't understand that until it took a while to get used to, okay, that's what Python means when it says equal. All right? It's very tricky. All right, so then if you keep doing this over and over again, right, it keep randomly updating of the 16 units. It will select, those units randomly, and it will keep changing. That's why I say there will be some flip-flops. And after a while, it will settle until the HD doesn't change anymore. The Hamming distance will stay fixed. Hopefully, the Hamming distance will fix at 0, meaning that it will be the same as your input. But you will see sometimes it may not. Okay? It may fix at not 0 Hamming distance, which means that the system you give it something that looks like a cat, and it struggles for a while, and then it concludes that it's a dog. And it doesn't change. It it failed. It cannot remember that, wait, this is supposed to be a cat. Why do you keep saying it's a dog? It means there's something, this system, for whatever reason, cannot retrieve the content addressable memory effectively. Okay? So it might happen. But it will do it dog, it will keep saying dog for 30 times, and then you have to stop. Okay? So that's what this means. So after it runs through this testing loops, iterations, it will return to you its series of A's, the E's, the energies, the Hamming distances, and any flags it may have had. Okay? So these are the two key functions. The function to implement the Hebbian rule, which is the trainnet Hopfield I have here. You can call it whatever you want. This is just what I did. And it requires an initial weights array, either a train one or a scalar one if you haven't trained anything yet. And of course, the information you want it to remember. You want to save this data, and use this one or whatever machine to save it. Okay, that's the train net. Now I'm going to retrieve. I'm going to give you some new data. I want you to, and the file that I saved it in, which is the W, right? And I want you to retrieve, I have this part of it, I want you to retrieve the rest of it, and I give you about 30 iterations to do it. That's what this testnet does, using the binary ReLU way of functioning. Okay, so I have these two functions. Any questions? I set this up. These two functions will be what we use then for the rest of the assignments. Okay, you have time to go through yourselves, and we can also hash it out more in the lab. Okay, but just to orientate you, that's my coding. All right, so remember, right? The assignment is now, so I've set up the training binary autoencoder with the Hopfield network architecture and making it into a 16 unit with the threshold 0 and setting it up so that it has a settling criterion of 30 iterations. All that is part of, although I just say this in these few lines, you realize that translating it into the code is not so transparent. So I show you the code there so that you know that what this means is you have to do all this. This, define that, set up the simulation. Okay? All right. So then the other parts here following this, where am I here? Okay, here. The rest are visualization functions. So I want to visualize the W as a heat map. So just like just now the vector, I visualize it as the wash functions as heat map. Similarly, if I give it an array W, I can visualize it as a heat map. Okay, so this function visualize heat map using Plotly does the visualization for W array. It will be different from the input vector because inputs are binary, 0 or 1. Okay, W's are not binary. They have a gradation of values. So I can't use the standard 0 to 1 gray map scale. So I use this red-blue scale. That's just for me to set up so that my heat map makes sense. Okay, and you have to set some size so that it fits within your visualization. All right. And then define energy plot. I want to plot a time course of the energy. You will see that the energy, the kinetic energy, right, minus half WAA, and it is a gradient descent, it's negative. You will see it goes down. And if it keeps going down until some point, it doesn't go down anymore, which means that it has lost, it has used up all its kinetic energy. It's not going to go any less than that. Okay? And then also have a function to do the testing of distortion. This will come in later, okay, not yet, all right? So I'll come back to this later. All right, so now we are ready to run the simulation. What we do is we first specify my test data table or input is these wash functions. So A is equals to that fancy wash function, no problem. W, I'm going to set it up as W equals to, actually it should be 0 or 1. Yeah, it doesn't matter. Actually, it should be 0. Okay? So that it's an initial array of 0. Sorry, I said 1s, but it should be 0s. Okay? Or some original array and with 16 by 16 size, because our input units are 16 by 16. Okay? And we can visualize the array at first. So should I run this one? Yeah, I should, so that you can see how it starts, okay? So let me connect it, and then I run it through. Which means I need to go to the library. Here. Need this part. Need this part. I need this part. I need this part. This one. This one I'll come back to it later, but I need the A array inside, and I make this. Ooh. Let's do this. This will be nothing. It will be wrong, right? Because it is not working. But but if I do W is equals to this one, okay, just like this. This is meaningless. It's just going to be a set of ones, and then I plot it. Just to validate that my plotting works, right? So this is a whole array of 1. Everything is 1, you can see, okay? So coordinate 6 by 10 is 1. Everything is 1. 7, 12 is 1. Everything is 1, okay? Nothing special here. No, so nothing's fancy, all right? So I can skip this for now. Now, I want to train my Hopfield network with A. So A is the wash functions, all right? So I want to train the Hopfield network as A. So I'm going to set it first to 0, okay? So if I train it once, see this value here. Okay, so I trained it and then I visualize it. I train it, I visualize it. So this is how you work your code, okay? So no problem here. 0 to 15 is AI or AJ, right? And 0 to 15 is AI or AJ, right? So these are the weights. And you can see A0 and, oh, sorry, it should be, I believe it's this way, right? Yeah. I and J. Let's make this I and make this J, okay? So I equals J are all zeros, right? So if I go along the diagonal, you can see the Z values are all 0. Can you see? Correct? Okay, so yeah, 0 here, right? And everything off diagonal is non-zero, okay? Now these are wash functions. Can you tell me why you see here everything is -4 on this part? So this visualization already tells you something interesting intuitively if you have a grasp of the mathematics and the patterns. You can see very nice patterns, right? It's very orderly, isn't it? It's not random. Because why? What is the dividing? Can you see something interesting in the wash patterns? It's flip. Yeah, symmetric flip in mirror, right? So there's some sort of a dividing line in between around unit. This would be 8, right? Or 7 or 8 or 8 and 9 or something like that, right? Okay. Further within, there's flip, and within there's flip, and within there's flip. Okay? And remember, the training function is just AI times AJ. And as when they agree, then you +1. When they don't agree, then you -1, right? Correct? And then the D by D, the dW plus W is just summing all this +1, +1, +1, or -1, -1, -1, right? So where is it always going to be +1, +1, +1, and -1, -1? Always, in this case, is here. 4 times, or 3 times at least, right? And then here is going to be 3 times, here 2 times, here 1 time. It's going to be +1, +2, +3, or +4. Or -1, -2, -3, -4. Those will be your dWs adding up. So if you go to the heat map, here, that's why the maximum is -4. Because 4 states, I can maximally do the difference with me and every other neuron is going to, the maximum possible is minus 4, because it'll be minus 1, minus 1, minus 1, minus 1. But the maximum will be plus 4 somewhere, if there is. It may not be. Okay, so in this case, it's minus 2. Yeah, that's right. Okay, yeah. So, and then other cases, it will be 0. So you can see the ranges of values are plus 2, minus 2, 0, and minus 4. Okay, yeah, if you scroll around, you'll see, right? So the weights have been configured based on the input. You want my input to be the same as the output. Well, used through my weights. Well, the way to solve it when you do the asynchronous, it hasn't done asynchronous, when you do the dot product Hebbian learning, the way to solve this configuration is to have it such that I have given your Walsh functions, my central line dividing the mirror is going to be the maximum dividing these two sets that I see. And then within these two sets, I have some further subdivisions. So you can see this pattern kind of coming out. Okay? You don't have to appreciate too much about the specific numbers, but I'm just highlighting that if you visualize it, you see some interesting things. Okay? What happens if now, here, my weights now have a range of minus 4 to 2, right? Minus 4, minus 2, 0, and 2, correct? I now train these existing weights with the same Walsh functions again, but now I have a new set of weights. What will I get? See, deeper. Minus 8, twice, right? Then minus 4, plus 4, 0. So mathematically not surprising, isn't it, right? I'm just using my same weights and then I add some more. So in other words, it is W at time t minus 1 plus W at time t. So if I keep doing this again, 12, right? Then 16, right? Okay, so let's see if I keep doing it, what's going to happen? So I hope you realize something. There's contrast. At first, it's some difference happening, but as you do it more and more and more, here is always 0. Here, the difference becomes steeper and steeper and steeper. So repeatedly training your network in this way increases the contrast of their similarities and differences. Okay? All right. So that's just, so if I reset it, back to 0, go back to 1. That's how I can set up my functions. Okay? All right. So this is the training part and visualizing the effect of the training. Any questions about that? Okay. Then testing it. Now to test, I have to give it some partial, I can't give it cat. If I give it cat, then it will return to me cat, and I'll prove it, you'll see it, okay? But more interestingly, we said the test of the Hopfield or content addressable is if I give you partial, you can give me the full trace. I give you some address, you can give me the whole house, correct? So I have to have a way where I have my original A, the Walsh functions, but I damage it. I mess it up a little bit, so I distort the patterns. And this is where I need to load this one, the distort pattern function, which is that I have the original A, but I have a probability P where some of the original states will be flipped. So if originally A is 1, 1, 1, 1, 0, 0, 0, with some probability, I want to change one of those 1s to 0 or one of those 0s to 1. If the probability is 0, then the result will be exactly 1, 1, 1, 0, 0, 0. If the probability is 10%, then 0.16 probability, I will change one of those of the 16 with a 10% chance of changing to 1 or 0, depending. I'll flip it. Okay? So that's what this function does. Again, I cannot say AP equals to A. I have to make a copy of A into AP, okay? So that I don't change my original items. I still want those, right? But I now want some distortion of it. I want some distorted AP with some probability so that for unit in all of AP with some random probability that is less than or equals to P. This basically says that whatever probability P is from a sampling from a random uniform distribution, right, of zeros to ones, right? If the unit is 1, make it 0, else make it 1. Okay, this is the distortion function. So I want this one. I hope you get this. If you don't get this, you can offline digest it. It just always takes time to understand what it's doing. But what this means is selecting out of 16, each one with a p% chance, change it to ones or zeros depending, flip it, right? Yeah. Okay, so I have my flipping function, my distorting function. Now I want to distort test pattern. Let's do test pattern 0. So the first one. And let's do distortion 0. I don't want to distort anything. And so my test pattern is original, correct? So, but let's say I distort it with 0.1. 0.1, very low chance. Let's do it again. It does, okay? 10% of the time, it will do it. Okay. Right, very low, right? But let's do 50% of the time. See? Okay? Okay, so that's what the function does. But just to show you, okay, if I have cat, I now have trained the network on cat, correct? And now I test it with cat. Okay? So I use my test Hopfield with, this is where I have trained it with cat just now. And now I give it my test pattern, which is cat, okay? And I set my iterations to 1,000, okay? I can do it with 30, but I mean, let's do 1,000, doesn't matter, okay? And you remember it returns the output, which is the AT here, okay? And the energy and Hamming distance time courses, which I already have plotted, and any flags, all right? So, and I make it so that it will print the original test pattern, the distortion. In this case, there's no distortion, so the test and the distorted are the same. And its output, what the network then tells me it remembers, and the Hamming distance between the two, whether they are the same or there's some differences, and the plot of the energy time course. Okay, so these are some of the evaluation metrics I want to do. So I just run it. So the test pattern is 111,000. I didn't do any distortion, so the distortion input, the distorted input is exactly the test pattern. And not surprisingly, the network retrieves that, yeah, I remember you gave me this 111,000 and the Hamming distance is 0. And see, my energy was very fast. I go to 16. Okay, so not surprising. So now let's try distorting things by, let's see, AP. What did I do? Okay, sorry. So this was testing 111,000. So you don't believe me? Why don't we do test pattern 1? Okay, and again, no distortion. Test pattern 1 is 1111, 0000, 1111, 000, the next Walsh pattern, right? So we have this. Let's see if the network can remember it. Perfect, right? 100分. You can test it here like this. Again, it will be 100分, guarantee you, okay? No problem with things exactly undistorted. It will retrieve that element. Now, let's do when we completely mess it up. Let's start back to the easy case or the more visually, okay? So originally test pattern 0 is 1111,000, right? We implemented now a distortion of 0.5. So this is none of the test pattern that was trained, correct? So let's see how the model performs. Aha. See the energy? It's no longer just quickly settling at 16. It took some time to settle. But in fact, when it settled, its Hamming distance was 16. It's completely wrong. Okay? In fact, this was the original. This was the distortion. And it returned us exactly the opposite. It completely don't remember this thing. But no surprise, because we distorted it by 50% chance. So obviously it could retrieve either one. Correct? Okay? Now let's make it a bit fair. Let's not make it so difficult. Just 20% distortion of pattern 0. Let's see if it can do it. Not so good. Still. Okay? There's a distortion. But let's try again. Because remember, it's random updating. Oh, I don't think it's going to do any better. But let's try to make, oh, sorry. Let's see if we can make our weights a bit stronger, and then let's test it again. Still no luck. Okay, so it looks like this particular distortion is problematic for this network. Let's make it not so problematic at all. Okay, yeah, this is pretty close to the original, right? Let's see how it does, okay? Just 10% only. You must be able to remember it, yeah. So you see, if I test it on if my original was this, I distorted it 10%, it can fill it back for me. Correct? And then now the Hamming distance is 0 and the energy is minus 48 because I overtrained the network. Okay? Actually, I didn't need to. So these are, I'm just going through some ways to test and evaluate how my network, do I train it more? Do I tweak the distortion? And because it's random, does it mean that every time it will perform? Or like if I change this distortion again, this is perfect, right? So even 20% just now it failed. But let's say I make it not so serious. Does it work? No. But see, it can sort of, it bounces around. And it worked. In this case, it worked. 20%, just now 20% failed, no matter what. Now 20%, it still works. Okay? So there's an element of stochasticity. This is why I say, this is not guaranteed. You have a mathematical sort of guarantee that you will on average go to this range of responses, and you can feel secure that it has some close, our memory is not perfect either, right? So similarly, because of that, you have to play it out, and then you have to evaluate it over many configurations, over many metrics. You see all the metrics, and you tweak different settings. So, but that's how we have done it. We have instantiated a situation where we have a partial trace, and it retrieved the original trace, right? Sometimes, or most of the times, depending on the extent to which the partial trace resembles the original trace. So in that, our content addressable memory is like that as well. We see a cat. We see something that looks like a cat. We retrieve the whole cat. But if this something that looks like a cat is really more like a dog, obviously we will retrieve dog. We won't retrieve cat, even though maybe originally it was a cat, right? Okay? So this is, you see how this really just mirrors a lot of our psychology of our memory. Okay, so up to this point, any questions? So observe how it performs, retrieves all functions based on distorted inputs. Does it fulfill content addressable memory? Why do you think, why not? And then I have set this up as a way of visualizing things. There are ways, and you will need ways to do it better. If you go and see my unpublished paper, there are more advanced things that we do. We even do statistical tests. So you're like, so we run this over all probabilities. Over each probability, we run it 10 times, and then we calculate the mean and the standard deviation of when they are accurate or not accurate and all that. We can actually do statistical tests. So in other words, you treat this like a subject. And then you run many subjects with many different ability, and then you see if the population sample, the mean and the standard deviation are significant. The effects are significant, right? Same. So I hope you can see the mirror between the simulation and actual human data collection works. It's actually very similar. All right. Okay, so any questions about this up to this point about the training function, the testing function, the distortions, the visualizations, and then how you use it and how it fulfills the data table, the hypothesis, and the simulation goal. And therefore the psychology, the psychological mechanism conclusion. Okay, all good? So with that, we have arrived at basically up to this point. Actually, yeah, test your network, create patterns that randomly change from 1 to 0 with probability of 0. 0.1 we did, 0.2 up to 0.5. And as I said, you can do statistical tests by running each training pattern in each probability 3 times. So 0, we run each, there are 4 training patterns, so we run it 3 times, so there'll be 12 times. 0.1, 12 times. 0.2, 12 times. So 12 times 5, right? So 60 times altogether. And then you can, from this 60 times, so you can do it either by hand for me, like, I click it and do it 60 times. Please don't do that. Please learn how to do proper coding. Write your own program so that you can do all the runs for you and collect the necessary data one shot. Okay, loop over 60 times accordingly, like plug and play the code accordingly. And then, I said, make provisions for the network failing so that you don't burn your machine. Okay, so, and these are the things, really this assignment here is to guide you as what I just did so that you can also know what to do. Record the Hamming distance, record the iterations you had to run before settling, record the energy, and then optional, describe in graphic illustration, like show the test pattern, the result, and the Hamming distance and all that. Basically, characterize the performance of this network for the Walsh functions at different levels of test input distortions. That will be assignments questions 1 to 3. Okay? So you have this, you can go back and revise it next week in lab. You can try out already since you have the assignment. And next week in lab, you can try it, and maybe we can do an exercise where you show everyone, we go through what are your works, right? And we can use this future classroom. I can flip between, sharing, everyone can project their work and then talk about it, and we can discuss about your problems, your thinking, and what you think about the Hopfield network. And plus, more importantly, obviously in class we do that, no problem. What if you train it on a different set of Walsh patterns, like this one? Okay, so do the same thing, and then evaluate it. Then create random patterns. So in other words, nothing so organized as this. Just throw some random ones and zeros, and then see how it performs. Why? Because Walsh patterns are orthogonal. So meaning when you learn one, it doesn't interfere how you learn the other, right? Right? Remember the weights, we could so totally understand the weights, the nice symmetric matrix. Because when you learn Walsh patterns, one pattern is orthogonal from the other, and so they don't interfere. But in real life, cats and dogs have many overlapping features. They are not orthogonal. They have some commonalities, as opposed to other categories of objects or events, right? So more like random patterns, okay? And then do the same thing, and then explain the same thing. Then do something where you train it on something, then you train it on something else, additional 4. You train it on some 4 patterns, then after that, don't reset it. Keep training it on other 4 patterns. Now go back and test. So this is interference. Okay? And then create a base pattern like the original Walsh patterns, then create 6 training patterns by switching the original pattern randomly, okay, with some probability. But don't train it on the original pattern. Train it on those switching. See if it can get back the original pattern, which you never train it on. And think about what this means psychologically. Do we have some example of that, right? And yeah, so then try on these. Instead of 16, try on these 4-bit word instead of 16-bit word. Okay, and also try it for non-binary inputs. See if it works, or what might you have to do to make it work. What you think. I can guarantee you this will not work. At least it won't work as it is. You will have to tweak it, and it will not be obvious how you tweak it for now. Okay? Because this kind will require not just this current setting. You will need some additional thing. But I'm putting it there so you can see it for yourself, and then explain it, why you think it works or doesn't work. Okay? Yeah, so through these 12 questions, I believe you will get a very, very rich understanding of the Hopfield network. We will try it out in labs, and I hope you can see, actually, it's very fun, right? Because it's really like, yeah, our memories sort of work like that. And if this is really kind of like a model of our human memory, then what can it do that we know our human memory, behaves like that as well, right? Not just one aspect of the content addressable where we retrieve partial traces. Other things like interference, like retrieving non-learned things, like the richness of the feature sets and all whatnot things. Okay? Yeah, so that would be this Hopfield, this class of networks. All right, so any questions about this? Or a lot of questions. I tell you, yeah, it's this kind of thing. That's why I say I can lecture forever and tell you nothing beats that you just do it. Just do the assignment, follow through, and I give you these basic tools. See, I even have these simulations if you want. I don't go through the rest, but you can look through it. See, so I set it up for you so that I can do it like many, many times. But you may not understand it. So just only the first part, then you can use the first part. These other parts are me doing more fancy stuff, okay? And you can try it out later, or we can try it out next week, okay? But this is for you to play with. It's a playground for you to try it out. All right? So I will stop here for today. And then next week, as I said, please come back. Yeah, I forgot to ask. So everyone has submitted the assignment homework too, yeah? Anyone had issues? You forgot? No, last week. Never mind, try submitting it by today, tomorrow, this weekend, okay? Then you can do the next, then immediately please jump to the assignment 1. You can open it already. So please jump to assignment 1, and next week in lab, whatever assignment 1 questions you have as you are working through, and you can share, we go through, and then so that when you so that it will help you along in submitting your assignment 1 finally, which will be like when assignment 2 is released. Okay, so this is the way we're going to work from here on. It's going to be like that. Okay, any difficulties with that? No, okay. So I think it will become clearer as you go along, and I hope that this, you will find this beneficial for learning neural networks this way. Okay, so that's it for now, and Yeah, so this video will be put up, obviously, but as I said early in the class, my recommendation is every time before class, please look at the 2025 videos, and when you come to class, you can ask questions. The 2026 videos are more for, every year we might deal with slightly different things, so you can revise those videos. But don't go and look at last year's videos 3 hours, then look at this year's videos 6 hours, then next year 9 hours. I don't think that's useful. I think more like the resource is more for you to actually, when the videos are great because you can see the lectures ahead of time, and lecture time becomes more like we interact and hash out deeper issues. We can go deeper. We can go deeper that way, right? And the iterative updates are more for like sometimes we have new issues that we didn't deal with before because every year people ask different questions or it focuses on different things. So that's the way I would gear it, okay? So for next week, please, if you can, also look up last year's videos ahead of time and also work on the assignments, and we'll come and deal with it in the lab next week. All right, thanks, and we'll see you next week.